We'll start this lecture by establishing a corollary from Taylor theorem, which will allow us to establish in turn whether or not a function is equal to the sum of its power series, its Taylor series. So a corollary. Suppose that f nth of x is less or equal than c for all n greater or equal than 0 on the interval or and x inside the interval AB, where A is less than 0, less than B. Then f of x is equal to the sum of its Taylor series, and from 0 to infinity f nth of 0 over n factorial x to the power n for all x in AB. And to prove this, as I said, we're going to use Taylor theorem. And let's see, what does Taylor theorem tell us? That in this case, if I compute Rn of x for some fixed x in AB, then I will see, again by Taylor theorem, that Rn of x is the same thing as fn plus 1 of y divided by n plus 1 factorial times x to the n. And, right, so where y is between 0 and x, or x and 0 if x is negative. And so then, magnitude of Rn of x, which is equal to, let's see, what can be negative here? The nth derivative can be negative and x can be negative. So this would be equal to magnitude of fm plus 1 of y divided by n plus 1 factorial times absolute value of x to the power n plus 1. But we assumed here that all derivatives of my function are less or equal than c. So then in particular, n plus first derivative must be less or equal than c. So this whole thing is less or equal than c over n plus 1 factorial times x to the n plus 1. And somewhere in Advanced Calc 1, we proved that this quantity is going to go to 0 as n goes to infinity. Uh, the logic is really simple, right? Because if I have fixed x, then over here, I take fixed x to the power n plus 1. So I'm multiplying magnitude of x by itself n plus 1 times. So each time I raise the power by 1, I have to multiply by x. But if I look at n plus 1 factorial, on each next step, I'm multiplying by larger and larger integer, right, as I increase n. And so that means that eventually, so here, on the next step, I'll multiply, let's say, by x, magnitude of x, to get magnitude of x to the power n plus 2. And down here, I'll have n plus 2 factorial, so which is n plus 1 factorial times n plus 2. Then on the next step, I'll have to get x to the n plus 3, I'll have to multiply again by x, but the denominator I'll have to multiply by n plus 3 to get n plus 3 factorial. So that means that eventually I will start multiplying denominators by larger and larger numbers, larger than x. And so therefore the product must go to 0. And if the product goes to 0, so then from this I will deduce that the limit when n approaches infinity, what is the remainder? Rn of x was f of x minus Tn of x, where Tn of x is a Taylor polynomial, or a sum of the first n elements of a Taylor series, partial sum of a Taylor series. Now, f of x is independent of n, so this is equal to f of x, right? Because the limit of a constant in terms of n is that constant, minus limit n goes to infinity of Tn of x, and Tn of x is the nth partial sum. So this is k from 0 to n, f k of 0 divided by k factorial x to the k. And that limit, if it exists, is exactly the sum of a Taylor series, right? So f of x minus sum k from 0 to infinity, f k of 0 over k factorial times x to the k. And just to emphasize, so this is again the same thing as a limit n goes to infinity of Rn of x, right? If a limit of absolute value of Rn of x is 0, then the limit of Rn of x itself is 0. And I'm just going to put 0 over here. And so that means that this guy is equal to 0. And so the final conclusion is that f of x is the same as sum from 0 to infinity f k of 0 over k factorial times x to the k. And so then the corollary has been proved. Okay, and so now let's try to use this to do a couple of examples. We already talked about Taylor series for the exponential. So if I have f of x equal to e to the power x, then to get a Taylor series, I need to take infinitely many derivatives of e to the x and evaluate them at 0. So then f nth of x, right? Any derivative of e to the x is itself. So that's e to the x. So that f nth of 0 is equal to 1, right? And so therefore Taylor series for e to the x is sum from 0 to infinity. Derivative evaluated at 0 is 1, so 1 over n factorial times x to the n. Okay, so is e to the x equal to the sum of its Taylor series? How do we decide? We can try to use a corollary that I just established. So to see if e to the x is equal to sum from 0 to infinity of x to the n or over n factorial, we're going to try to use a corollary. Okay, so the corollary says that if all derivatives of my function are bounded by the same constant, then that will imply that these two things are the same. So, in this case, e to the x, so nth derivative of e to the x, is always equal to e to the x for all n greater or equal than 0 and x in R, right? Further, if I look at all x in R, right, then what would be the maximum of e to the x when x is in R? Well, clearly that maximum is going to be infinity, right? Because e to the x is unbounded on the right-hand side. So that means that I cannot apply the corollary on R because e to the x is not unbounded there, right? You can only apply a corollary if all derivatives are bounded by the same constant. But I can use the same trick that we used before when we established uniform convergence of power series. And the trick is going to be like this. So consider instead an interval let's say from minus infinity to some x0, right? Then max e to the x when x is between minus infinity and x0, this maximum exists, right? Because e to the x is an increasing function, so that maximum is e to the x0, right? And so therefore, because all derivatives are equal to e to the x, it follows that absolute value of nth derivative of f evaluated at x must be less or equal than e to the x0 on our interval from minus infinity to x0. And so then, from the corollary, it follows that e to the x is equal to the sum n from 0 to infinity, x to the n over n factorial, right? So because all derivatives are bounded by e to the x0 on the interval from minus infinity to x0, then that immediately implies that e to the x is equal to the sum of its series. But then we discover that x0 is a totally arbitrary number. So instead of, if I use x0 1, I can then use x0 equal to 7. Then I can use x0 equal to 1000 and so on. So I can make x0 arbitrarily big. So since x0 in R is arbitrary, then e to the x is equal to the sum of its Taylor series on a number which extends, which has an infinite extent, arbitrarily large extent along x-axis. And so that means that I can deduce that the statement is actually going to work on the entire real line. Right? So because e to the x is equal to the sum of its Taylor series on the interval from minus infinity to x0, I can keep extending x0 more and more to the right, and at the end of the day, I'll recover the entire interval from minus infinity to infinity. So e to the x is the sum of its Taylor series for all real x. Okay, let's try to do the same thing, but for the function example number 2. A function f of x is equal to the log of x plus 1. So where is f of x equal to the sum of its Taylor series. Well, let's compute first what a Taylor series is, actually. So for that, we will need all derivatives of f, right? So ln of x plus 1, derivative is going to be 1 over x plus 1 or x plus 1 to the minus 1. F double prime of x is derivative of x plus 1 to the minus 1, so that's minus 1 times x plus 1 to the minus 2. F triple prime of x is, and notice that in this case I'm not going to simplify the expressions because I would like to see the patterns of what I'm getting. So minus 1, then minus 2, x plus 1 to the minus 3. And if I continue in this fashion, then what sort of thing am I going to get for the nth derivative? Well, so the pattern appears to be first derivative power minus 1, second minus 2, third minus 3. So there will be x plus 1 to the power minus n. What else? There are some minus 1s here. So for the first derivative, you have plus 1. Second derivative, minus 1. Third derivative, 2 minuses plus. So each odd derivative will have a minus sign. Each even derivative will have a plus sign. And we can express this statement by saying, let's take minus 1 to the power n. Then if n is odd, you get minus n is even, you get plus. Okay, and furthermore, let's forget now about minuses. For f double prime, I have 1. For f triple prime, I have 1 times 2. For f fourth prime, I'll have 1 times 2 times 3. So this is n factorial, which ends at 1 digit below n. So n minus 1 factorial. And then times x plus 1 to minus n. And from this, I can quickly evaluate fn at 0. So at 0, x plus 1 is 1. So x plus 1 to minus n will be gone. And you just have minus 1 to the n times n minus 1 factorial. Sorry, n is on the top. Okay, and so then because I know what nth derivative at 0 is going to be, I can now compute the Taylor series. So Taylor series is going to be the sum n from 0 to infinity, then fn of 0, then n factorial, and then x to the power n. And I know what fn of 0 is, so this is a sum from 0 to infinity of minus 1 to the n minus 1 factorial over n factorial times x to the n. And then recall that n factorial is a product of all integers up to n, so n minus 1 factorial is a product of all integers up to n minus 1. So the circle stuff is completely inside the n factorial, and in fact, the only extra term in the product below is n, right? So all terms will cancel out except for n itself. And so you'll get that this is equal to the sum n from 0 to infinity of minus 1 to the n divided by n times x to the n. Right? And so this is a Taylor series for ln of x plus 1. Okay, now where does the series converge? What's the radius of convergence of the series? I can deduce that by using a ratio test. So we need to take a limit as n goes to infinity of n plus first term, absolute value of the n plus first term, divided by absolute value of the nth term. When I take absolute value, minus 1 is no longer going to be relevant. So I have x to the n plus 1 divided by n plus 1. And then divided this by nth term is the same thing as multiplying by n over x to the n, and you take absolute value. Okay, so simplifying this, the limit n approaches infinity. X to the n plus 1 over x to the n, that is just x. X is the only thing that can be negative here, so absolute value of x times n over n plus 1. And as n goes to infinity, right, x I can pull out, and n over n plus 1 goes to 1. So this is absolute value of x. It has to be less than 1. So that means that the radius of convergence is 1, right? So that means that this log function is defined, that the Taylor series for the log function is defined on an interval from -1 to 1. So r is equal to 1, and then x is between -1 and 1. All right, so how can I check then if the function is equal to the sum of its Taylor series? I can try to use a corollary again. So now use the corollary. Let's try to use a corollary. So how can I use it? Let's see. Once again, what is the nth derivative of f of x? In this case, it's that, right? Let's copy. F nth of x is equal to this quantity. And what do I want from it? I want this quantity to be bounded, right, for all x and for all n, bounded by the same number. So is that going to be true here or not? Probably not, right? Because how can I write this down again? This is, in fact, I'm interested in the magnitude of fn of x, so let's take magnitudes. And so this is equal to -1 I can drop, and -1 factorial divided by x plus 1 to the n, right? And we were just talking about the fact that if I let n go to infinity, then the expression in the denominator basically grows with just multiplication by x plus 1 at every next step, right? So if n gets bigger by 1, then the denominator gets multiplied by x plus 1, but numerator gets multiplied by n minus 1 on each step, right? So n minus 1 is getting bigger, x is not getting bigger. X is exactly the same. So it means that as n goes to infinity, top is going to grow faster than the bottom. So this goes to infinity as n tends to infinity. And so that means that there is no common C that bounds all derivatives of f. And that means that I cannot use a corollary. So in this case, I have to invent some other way of estimating the remainder. And let's see if we can succeed with that. So on the other hand, given some x between -1 and 1, by the Taylor's theorem, what is the remainder? So Rn of x should be should be equal to the n plus first derivative of f, right? So what is the n plus first derivative of f? If this was nth derivative of x, f of x, then n plus first derivative is, you just replace n plus 1, n by n plus 1. And if you do that, you get minus 1 to the n plus 1. Then you get n plus 1 minus 1 factorial, so that's n factorial. And then x normally is x plus 1, the denominator is x plus 1 to the n, so if I compute the n plus first derivative, then this would be x plus 1 to the n plus 1, right? Again. All right, so except that I need to evaluate the n plus first derivative at y, right? Because that's what my remainder formula tells me. So this whole thing is f(n) of 0. So I need to divide this by n plus 1 factorial and then multiply by x to the n plus 1. Right? So once again, the remainder is n plus first derivative evaluated at y divided by n plus 1 factorial times x to the n plus 1. And of course here I should be able to simplify this. I have n plus 1 factorial on the bottom and I have n factorial on the top. And in fact I'm going to work with absolute value of the remainder. So that means that I can drop minus 1 to the n plus 1. So on the top, the only thing that remains is absolute value of x to the power n plus 1, right? Because minus 1 to the n plus 1 is gone. N factorial cancels out with a part of n plus 1 factorial. And then on the bottom, what can be in principle negative? Actually nothing, because remember, x is between 0 and 1, right? And y is between 0 and x. So if x is between minus 1 and 1, then y also should be between minus 1 and 1, and not equal to minus 1 or 1. So that means that y plus 1 is always a positive number, so I don't need the absolute value here. So y plus 1 to the n plus 1. And there is one more thing here. If I cancel n factorial from the top, then I have 1 plus 1, n plus 1 remaining on the bottom. All right, and one more thing. So I have two guys to the power n plus 1, something on the top, something on the bottom, so I can combine those to be absolute value of x over 1 plus y to the power n plus 1 times 1 over n plus 1. Okay? Now, if I want to see what is going to happen to this quantity when n goes to infinity. So clearly 1 over n plus 1, when n goes to infinity, that will go to 0. What about this factor? Well, if this factor inside, right, absolute value of x over 1 plus y, if this is less than 1, then once I raise a number less than 1 to the power n plus 1, and I take n to infinity, then this will go to 0, right? So then the circle term goes to 0, this term goes to 0, so overall the remainder will go to 0. On the other hand, if magnitude of x is larger than 1 plus y, then in that case, of course, numerator is greater than denominator, you get a number bigger than 1. And if I take a number bigger than 1 to the power n plus 1, that will go to infinity. And because it's an exponential growth, then this term is always going to beat this term. So whenever magnitude of x is bigger than 1 plus y, then remainder would not go to 0. And when magnitude of x is smaller than 1 plus y, then the remainder goes to 0. So goes to 0 as n goes to infinity if absolute value of x over 1 plus y, absolute value of x over 1 plus y is going to be greater than 1. Sorry, less than 1. All right, so when would this be possible? So first of all, if x is greater than 0, right? If x is positive and y is between 0 and x, then 1 plus y is going to be larger than x, right? Because if x is between 0 and 1, so let me write this down. So if x belongs to the interval from 0 to 1, then y belongs to the interval from 0 to x, which is still between 0 and 1. And so in that case, so that x then must be, absolute value of x is the same thing as x. X is less than 1, so certainly x is less than y plus 1, right? And so therefore magnitude of x over 1 plus y is going to be less than 1. And actually, if x is negative, then I have to do a little more work to figure out if this relationship holds or not. So I'll encourage you to try to see that on your own. But for sure, from this we can conclude that ln of x plus 1 is equal to the sum of its Taylor series, which was what? Which was minus 1 to the n over n times x to the n. And by the way, I have to be careful here. I cannot include n here, right? So I cannot include n equal to 0, right? Because if n would be equal to 0, then I have to do something special, right? So if n is equal to 0, then f of 0 should be ln of 1, right? And ln of 1 is equal to 0, so for 0 I forgot to do that. For 0 I have to use a special formula. So let me modify this a little bit. So this is true if n is greater or equal than 1, and f of 0 is 0 because then you're taking log of 1. And so therefore, when you're writing down your series, you're not starting from 0, but you're starting from 1, because at 0 you get no contribution. So that's what we got. And so ln of x plus 1 is a sum n from 1 to infinity minus 1 to the n over n times x to the power n. Okay, and this is true if x is greater, if x is equal to 0, of course, this is always true, because x equal to 0 is the center of a series, and at the center of a series, it's always equal to center of a power series is always equal to f of 0, so always the function is going to be equal to its Taylor series at the center of a series, which in this case is 0. So greater or equal to 0. One more example, example 3. Let's do a series for cosine of x. So again, the same question. I want to find the Taylor series and determine where f of x is equal to the Taylor series. So find Taylor series and determine for which x Taylor series is equal to f of x. So item number 1, find the Taylor series. For that, again, I will need to take derivatives. F of x is cosine x. F prime of x is minus sine x. F double prime of x minus cosine x. F triple prime of x is sine x. And finally, fourth derivative is cosine x, right? It's again exactly the same as your original function. So that means that starting from this point, you're simply repeating the same pattern over and over again. Okay, so then what is f of 0? F of 0 is 1. F prime of 0 is going to be 0, right? Because sine of 0 is 0. F double prime of 0 is minus 1, because cosine is equal to 0 and there is a minus in front. F triple prime of 0 is 0 because it's sine. And then fourth derivative at 0 is the same as function at 0, so this is again 1. So that means that we're going to retain only even terms of Taylor series, right? All odd terms with odd powers of x, are going to have 0 coefficients, so they will just vanish. And so the series is going to look like this. Let's see. Let's actually write it out, and then we'll figure out the expression. So how does my Taylor series go? It's a sum n from 0 to infinity, fn of 0 over n factorial times x to the n. So if I write it out, this is f of 0 plus f prime of 0 x, f double prime of 0 x squared plus etc. And now let's substitute f and its derivative into this. So this is equal to f of 0 is 1, f prime of 0 is 0, f double prime is minus 1, and I'm missing, of course, the fact that I'm dividing by the factorial over 2 factorial. So then f double prime of 0 is -1. So -1 over 2 factorial x squared. F triple prime is 0. So then I have f fourth with a plus, 1 with a plus sign. So 1 over 4 factorial x to the fourth, then minus plus, etc. So you have an alternating series like this. And now if I want to write this by using sigma notation, you can do it in the following way, and goes from 0 to infinity. So I see x squared, x to the 0, x squared, x to the fourth, right? So that means that always I'm going to be dealing with even powers. So I'm going to use n to count even powers. So then what is power of x? Then it's just 2n, right? N is any integer from 1 to infinity, but then x to the 2n is going to be an even power always. And I am dividing this by the same number as a power, factorial. So 2n factorial, right? So that is going to be a product of all integers up to 2n. So that's a Taylor series. For cosine x. And now let's try to figure out where this is equal to the sum of a Taylor series, where the function is equal to the sum of a Taylor series. And for that, again, maybe we can try to use a corollary. Let's take derivatives of my function. So derivatives are always plus or minus sine or cosine. And what I know about sine and cosine, that this is a number between -1 and 1. And then minus cosine or minus sine or sine itself, they're all functions with values between -1 and 1. So therefore, if I take absolute value of fn of x, I can guarantee that this is less or equal than 1 for all n greater or equal than 0 and all x, all real x, right? And so therefore, by the corollary, cosine of x is equal to the sum from 0 to infinity of a Taylor series x to the 2n over 2n factorial. And this should be true for all x in R. And notice that in this case, I don't need to determine the convergence of this somehow separately, because if the remainder between the function, and the function has finite values, the remainder between the function and the power series always goes to 0 at all x, that means that the sum of a series is equal to cosine x for all x. So that means that the series converges for all x in R.